All right, we're at Northwestern University, the FRC workshop, and I'm Keith Hall. I'm the first senior mentor for the state of Illinois. And I'm going to talk about control systems, feedback, sensors, that kind of stuff. And I have a little outline of what I'd like to cover today. First of all, I'm going to talk about the more common sensors that we see and use in FRC and kind of show you how we classify them. Very, very brief overview in control theory, like only a couple, 3 slides. Now, I'd say it's very brief because, trust me, control theory is a developing discipline right now. You could probably get several PhDs from Northwestern on control theory. And we're not going to get too deep into it, but we are going to talk a little about it so you know what it is and can read some of the graphs and stuff. And then we're going to apply that. So we're going to take the knowledge of control theory and some of the FRC sensors, and I'm going to show you how to use a feedback control system to make your robot perform a lot better, a lot more accurate, a lot more consistent, that kind of thing. And it's called PID. If you haven't used PID, you're going to want to after this. So, you like my picture? This is why it's important when you have the marketing meeting and somebody from engineering show up. Otherwise, things can get embarrassing. So let's talk about sensors. In FRC, we generally classify sensors in 2 broad categories, either digital or analog. And that's because you have places to plug in either digital or analog sensors. Now, there's many, many different ways you can classify sensors, and there are many thousands of different kinds of sensors. There is a 3rd class, and we do actually use some of them. For example, the camera is a very, very complicated, very complex sensor, and it uses a standard protocol, in this case Ethernet. You'll also find, if you dig into the documentation on the Jaguar motor controllers that we supply, it uses CAN, which is another small computer system protocol. But we're going to really focus just on the digital and the analog for today. So what is a digital sensor? Well, it's anything that you plug into. This is the, what is it?
Digital sidecar.
Yeah, this is digital sidecar. And they plug in here. That's for servos, and you plug in your blinky light goes over here, right? You know about all that. So anything that plugs in here. And we say that digital sensors are used for event-driven programming. What does that mean? I think the best way to describe that is when we teach the basics of programming to like the Lego League kids, one of the first things we teach them is how to put a limit switch on the front of the robot, and we have them drive the robot until it hits the wall, and then it stops, and then make them back up and turn around or something like that. And the event is it hits the wall. Okay, now the robot has no idea it's getting nearer the wall. It only knows once it hits. So it's event driven. So as you can imagine, it tends to be rather coarse feedback. It's not real precise. You don't get a lot of information. You just get yes or no. And you know, on the positive side, it's very simple, very easy, very inexpensive. And I would say that the vast majority of them are really easy to mount on the robot. And there's some flexibility, but you are really quite limited. The most common one, of course, is the limit switch, which I'm going to hand these around. There's all kinds of different limit switches. One of them's got a clear side so you can actually see the contacts open and close. And my favorite, the binary, it's either a 0 or a 1. That's a great idea for a switch. Either it's open or it's closed. And those are really the only choices in digital. So I'm going to hand this around so you can see they come in all different sizes. They have nice little mounting holes, so they're really quite often very easy to attach to a robot. Never have any problems finding the right size. You know, I just kind of strung them together. Now, you can wire these things different ways, normally open and normally closed. And which way should you do it? You want to do it in such a way that you're not going to have a real problem. What do I mean by that? Well, imagine that I have a limit switch. I've got an arm that comes down, hits a limit switch and stops. Now there's several ways you can wire that. One way would be, for example, I could be connected to normally closed. So when I'm looking at that sensor, it's high. In other words, it's seeing. And then when it goes low, you tell the arm to stop. But the other way to do it would be to have it connected to normally open, and then it comes down, and when the signal goes high, you have it stop. Now, depending upon what happens if the arm goes too far, which one would be better? One that cuts the electricity to it? Why? Why?
If it goes too far, you might break, you might hit something else instead, or?
Yeah, if you wire it so that it actively has to change, so that the power is there, and you turn the power off, and that's when it stops. If for some reason the wire gets cut or gets disconnected, the arm just won't move, right? You follow me? But if you have it the other way, the arm can just keep going. The switch is unplugged. It'll never get a high signal. So you need to think that through and look at that carefully so that you don't accidentally mount it or program it in such a way that the robot can destroy something. That could set you back a couple matches. Now it is true, if the wire comes loose, you might lose that particular match, but I'd rather lose one match than the whole mechanism. So there is a little bit to know about digital switching. Now my favorite digital sensor is an encoder. I love encoders. They're basically rapid on-off switches, and they detect some kind of physical profile, like gears in a T, or some of them have little colored black and white, what would you call them? Like axles, splines that go around on the wheel. And all it really does is it tells you how many blips you get, and you measure that per unit time. And you get some idea if you have more blips per unit time, the wheel's going faster, or it's gone around so many times if you know how many counts, how many teeth in the gear, for example. Generally, you're using it for a relative position. That is, you're not using it to know exactly what degree. But you can do it that way. You can get an absolute position. If you, for example, put an encoder on an arm, have it go down, stop a limit switch, then you reset the encoder to 0. Now if you go this way and you're counting, you know how far. And you can go back and forth as long as you're really careful and make sure you count all those clicks. But there is a better way to do it. So generally in FRC we use these encoders for relative. And I think a good example of that is, if you haven't done this, you should do this over the summer. Make the robot go in a perfectly bullet straight line. It's a fun exercise. So you need 2 encoders, one on each side of the robot. Assuming you have, like a tank drive or, something where you've got one motor makes one side go and one motor makes another side go. And you assume, of course, that you haven't got one wheel in the air or you're not driving over banana peels. It's really very simple then. You just periodically go out and look at the counters, compare them. The one that's lower, well, you want more power to that one, bring it up. Or the one that's higher, maybe reduce the power, or you can do both. And you can explain it. You see how easy it would be to make that thing go? Now, how often do you do it? Well, with a computer, you can do it 2 times a second, 5 times a second, 10 times a second. Experiment with it. Trust me, you're not going to stress out the equipment we give you by having it check the encoder counts 10 times a second. It can do that quite easily. So this is a fun thing to do. Now you can get creative with this too, because, well, what if I wanted it to go straight for a little while and then have a nice gradual turn? If I knew the ratio of the counts inside and outside, I can do that. So you can actually use encoders to do quite complicated motion and, show it to friends and They could do cool things that nobody knew you could do. So I think we almost always supply some kind of encoders with the kit. I'm not real keen on some of the designs we've had the last few years, but you can buy these. They're not that expensive. Or you can get or find in junk equipment. This is a little, one side's a light and another side is a light sensor. And then you can just take like a lid from a coffee can, poke holes in it every so often, whatever. You build your own. They're very inexpensive. You can buy these, less than $1. So I encourage you to experiment with those. Now, some of the more advanced ones are called quadratures, and with quadratures, it's a little more involved. I'll let you read more about those. But not only can you tell how fast or how many times the rod has gone, it can actually give you the direction. It can tell you if you're turning clockwise or counterclockwise. Yes?
What are your thoughts on the encoders that have been provided with the kit of parts, like the AndyMark, Tough Box? Do those work well? I mean,
Do they work well? Yes, they do once they're installed. They're incredibly tiny, and I find them, I have bifocals, I find them difficult to work with. I like working with the bigger things. That's why I make my own. Like I said, there's many things, and you don't have to spend a lot of money on these things. But I would prefer probably to make my own. So let's switch now. We'll talk a little about analog sensors. They plug into a different board, the analog breakout board. This is the one where if you don't have the jumper, and I love this picture, it doesn't have the jumper installed. And you don't get voltage readings. And if you try to put a robot like this on the field, you're going to have the FDA is going to come over and talk to you. What's wrong with your robot? We're not getting a voltage reading. So be sure you put the jumper on there. But anybody know where I got this picture from? LabVIEW. There's examples in LabVIEW, and we'll show you where you plug all the wires in. Now, analog signals are much finer, and we tend to use them instead of an event. We tend to use them to find out what's going on in real time. So they do tend to be a little more complex. They are a little more fragile, which just means you need to think about where you're placing them on the robot so that they're protected. And they do cost a little more sometimes. However, the entry-level ones are really quite inexpensive. Positive side is there's really no limit to what you can do with analog sensors. It's limited only by your imagination, which I like those. The most common one is a potentiometer. Everybody know what potentiometers are? Variable resistors. I don't know why they don't just call them variable resistors. I have some examples in here. They usually look, something like that, like the picture on the screen. They have a knob that turns. They also come, these are called single turn, by the way. And by that it means about 270 degrees. They can't go 360. It just, if you try that on the robot, you just snap them right off. They also come in multi-turn, which I have some small samples of multi-turns. They're almost too small for robotics. You would want to buy the next size up for an FRC robot. And then you can also get them in a sliding, and we have used these like on a claw system, so we would know when the claw was closed or when it was open. So instead of having to make the driver, open, close, give them two different buttons, we would keep track of what status it is, and they just had to push it, and whatever status it was, it would do the opposite. So we make it a little easier for the driver to operate it. Now the way these work, I always, I'm going to pass these around to you. Feel free to dump them out and look at them if you want. When I show this diagram, and the in is hard to see, so that's the 12 volts or the 5 volts from your robot in, and it goes across this element, which is represented here, and it goes right to ground. And I've had students say, well, Mr. Hall, that's a short circuit, isn't it? Yeah, it is. But do resistors resist voltage or current? Do they teach this? They don't teach this in high school. Do they? Okay. So when you have a circuit like that, voltage gets used up. Voltage is like potential. In fact, it is. It's potential difference from one to the other. It's similar in a concept to like potential energy. So if I have something really heavy and it's up here, it has more potential energy. But down here, you can't, it has no potential energy. It can't fall any further. Voltage is similar. It's not potential energy, it's just potential. But when it's at the top, it has that potential. When it's at the bottom, you've used up all the voltage. So this would read, you know, if I had a meter, you know, that would read like 12 volts. This would read 0 volts, right? Because it goes through and it's all used up. Current runs like a river through that whole thing. But since resistors resist current, the amount of current here is really small. How small is small? What's a safe current? You know, I see some of these numbers in physics books and they kind of scare me. You know, you get the answer, it's 14 amps. That's dangerous. When you're working with this, you want to use like 10,000 ohms or 100,000 ohms. So let's say you have 10 volts. Anybody remember the rule that connects volts and current and amps and resistance? Anybody know that one? Ohm's law? V equals IR. So if I have V equal IR, or I equal V over R, well, if voltage is 10 and resistance is, say, 100,000, how many amps do I have? 10 divided by 100,000 is 3 zeros and a 1, right? That's a safe volt. That's a safe current. It would maybe take, if you connected A and B directly to your battery, it might take it a couple of weeks, do you think, to drain all the energy out of that battery? So it is a short circuit. Now the other thing about voltage is if you catch it halfway, you can catch it where it hasn't quite fallen all the way to 0. It's kind of like stopping it here. And so as you move this wiper around, it's the same as this, and you get different voltage readings depending upon its position. And then we have the circuits are built into the C-Reel that convert that different voltage into a 14-digit number. I like that. That's so much precision. And based on that, you can get a good idea. You know, when the arm is at this position, you'll get a certain amount of voltage from your potentiometer. And you know, if you go down and come back to it, it's going to be about the same. There's going to be a little variation. By the way, always use linear. There's two kinds of potentiometers out there. And so if you order them in catalogs, you'll see some of them say logarithmic. Those are volume controls. You know, hearing is logarithmic, right? Decibels. So to be twice as loud, it has to be, what, 10 times the power? You don't want to use those on robots. You want to use the linear ones so you get a nice linear progression. Any questions on potentiometers? I'm going to go to this one right here. This is the downside on potentiometers. They are somewhat challenging to attach to robots because most of them are made to be like volume control, where a human will turn the little knob. And they can be quite fragile. If you turn them too far, they will snap right off. On the positive side, they're not very expensive. The ones you're looking at there, I doubt I paid more than $1 for any one of them. But I have seen, if you have access to a lathe and you want to mount it on a pivot point, I've seen them hollow out a bolt and then on the hex flat side of the bolt, drill and tap that for a set screw. That works kind of well. I have seen people put gears or parts of plastic gears on the arm or the rotating mechanism and then mounting another gear onto the potentiometer. That works pretty well. So I've got a couple examples of how you use it, move an arm to an exact position. We're often, hanging things or shooting things, lift an elevator, elevate something to a protect height. You want to always try to give the driver as many advantages as possible by automating as many things as possible. And you definitely want to use as many sensors as you can. Now we almost always get an accelerometer and a gyro, and I'm always disappointed how few teams use it. These are some cool things, and by the way, these are, I say some of these get expensive, these are fairly expensive. Gyroscope, I think, if you go out in the open market, they're $35 to $50. The accelerometers are 10 to 15. So, compared to $1 for a potentiometer, they are relatively expensive. And, they are some really cool things. What do we use accelerometers for? Well, I like to use them mostly for telling if something is level. If I have an arm come up and I want it to stop at a particular point, put the accelerometer on there. Now, if I want it to stop at an angle, I put the accelerometer at an angle. Everybody understands now. If I have an accelerometer that's level, it won't measure any acceleration horizontally, right? But if I tip it, it will measure an acceleration. Why? What's it measuring? This is a physics one. Gravity. You ever hear people say the force of gravity? It's not a force. Gravity is acceleration. What are the units of acceleration? Meters per second squared. What's gravity? 9.8 meters per second squared. It's an acceleration. So if you put an accelerometer on there and you want to measure acceleration this way, you better get it level, because if you have it tipped, it's going to be adding the component of gravity in that direction. But the practical upshot is, again, if I have an arm and I want it to stop right here, I just mount that so that it's level at the point where I want it to stop, and then I can monitor that signal, and when it gets to level, I stop the arm. You can also use it to measure acceleration, of course, dynamic. For example, vibration, that's what we use them a lot for in industry. You've got a big piece of equipment that's got moving parts. You put an accelerometer on it, and you basically program in some limits so that it shuts down if you see too much vibration. That way the poor machine won't shake itself apart, or it's prevented from that. Probably not very useful in FRC. Shock measurement though, some of those are kind of fun. We've done this on a couple teams. You put the accelerometers on there, and you start a log file on its data, and you let it run through its normal courses, and if you hit, you'd be surprised how many G's. I've seen 14 G's of acceleration. Everybody had calculus? Anybody had calculus? Long time ago? Okay. Well, you can use an accelerometer to give yourself not only your velocity, but also your position. Now, I'm telling you this because it's possible and it's in all the literature. However, the processing power to do that is pretty taxing, and we're going to ask you, even if you understand that and know how to do it, please, consider not doing that, because you're going to use up a lot of resources on the C-reel, and we really do need those for things like talking to the field and such. But you can do this, and if you are not using the robot on the field, it is also kind of fun. You have all the icons, for example, in LabVIEW to do the integration. You have an engineering Mentor. It's a fun thing. You can use the accelerometer to measure a distance. Okay, the gyro. Anybody ever build, what do they call them, Mecanum wheels? You ever done those? So you have, each wheel has an independent motor, and they've got rollers around the wheels, and they're at an angle so that you can, roll forward and backwards just like tank drive. But if you do certain motions, you can get the wheels to turn in opposite directions, so it corkscrews, and it allows the robot to go sideways without turning. So you have this robot that is sitting in one place, it can go forward, it can go back, it can go left, right, without turning. If you try that, we supply some standard code, I believe, in LabVIEW, and I'm not sure if we do in Java or in C++. Does anybody know? Okay. If you try to do it without a gyro, it's a fairly uncontrollable robot. The reason is the gyro will tell you how much you rotate. It'll give you some indication of, are you going in a straight line or are you drifting this way? It'll tell you if you're turning or, and oh, by the way, we're only using the yaw axis. You don't want to use roll or pitch in FRC because that means your robot's tipping. Okay, so we're only using one of the three axes. By the way, the kit apart gyro, if you turn slowly in autonomous mode, and by slowly I mean like this, it works perfectly. If you turn like that, yeah. So go easy on it. Getting back to the Mecanum, what the software is doing is it's taking the data from the gyro and comparing it to the angle that you're moving the joystick constantly, like maybe 10, 12 times a second. And then dynamically adjusting the power to all four wheels so that the robot is moving at the same angle that you're moving the joystick. If you do not have the gyro on there, you're going to find it's really hard to steer that robot, and it's going to want to do all kinds of fun things. And again, in LabVIEW, if you just plug it in, if you haven't done this, it's fun to do. Put it on there. There's a little application. I think it's got a 360 indicator on it, and you plug the gyro in, and you can grab it, you can turn it, and the little needle goes in the direction you're turning the gyro. The final one in analog sensors is, we call them pingers in FRC. They're ultrasonic. Now, I've seen these used for a lot of things. They work really well at one thing. They find really big, flat, hard objects. Don't try to use them to find balls. Why not? If you have like a soccer ball,
Small. And it moves.
it moves. What else? It's rounded, yeah, so the sound hits it and deflects off. It doesn't bounce straight back. You want something flat. The other thing, as far as I know, you cannot use an ultrasonic rangefinder. It cannot detect pillows. Why?
Sound goes right through it.
What?
Sound goes right through it.
Goes right through it, or yeah, you ever been mad at somebody and go scream in your pillow? It absorbs the sound, right? So the energy goes into the pillow and it just gets dissipated and all that fluff. By the way, please don't use these in your pets. If you turn these things on for your family dog, if they're going to start howling, it's a really high sound. Dogs and cats can hear this. It's really painful for them. It's just not nice. So remember that when you're using these things, make sure the family pet is somewhere where they're not going to be disturbed. Okay? Now, a couple things about control theory. What is it? Well, it's the math, the science, the engineering of making things do what you want them to do instead of whatever they would like to do or whatever they normally do. And of course, the The opening textbook always talks about open loops and closed loops. What's an open loop? An open loop is you set it and you hope it gets there. Good example of that is when you go target shooting and you pull the trigger on the bullet. Once the bullet leaves the gun, there's no control. You just hope it hits the target, right? There's no way to steer it after that. Closed loop is what we're using in FRC. Closed loop is you have some kind of feedback, be it a sensor on a robot or the human person. You're actually part of, in teleoperated mode, you're part of that closed loop. You're providing the feedback to guide the robot. So we want to do it, we want to have the sensors, give us some information so we can do something about it and make the robot do what we want it to do, not just kind of randomly wander all over the place. Now, you'll see diagrams like this. And some of these get pretty elaborate and pretty confusing. So I just wanted to show you the basic flow. And by the way, electrical engineering, it's always input, process, output over here. Input, process, output, right? Okay, I don't think I've ever seen that in a textbook where they explain that. It's implied. But have you ever seen LabVIEW? The inputs have a string pointing that way, right? Processes have things on both sides and outputs on this side, so that they force you to follow that convention. So anything input, process, output goes that way. So feedback is this whole thing. You have this in the opposite direction. And if you're not used to looking at everything has to flow from left to right, it might seem, what's the big deal? So this one goes the other way. So it is kind of a big deal if you're an electrical engineer and you see something going that way. It kind of rings a bell. Hey, wait a minute, this is different. And so you have this flow of control. You put output to your Jaguars. You have an encoder that gives you some measurement. That's your sensor, and it's some kind of data that your computer can react to. So I want you to understand that really in terms of computer programming, there's some pseudo computer code there. Those two are equivalent. It's doing the same thing. And the basics of robotics is you get your data, crunch it, make sense of it, put your output, repeat. Get it, crunch it, put it, get it, crunch it, put it, get it, crunch it. Continuously, continuously, continuously. Now in FRC, for control theory, what we use is PID. What's PID? Anybody use PID? We're going to derive it. We're going to show you how it solves so many problems and makes your life so easy. But it's just, I want you to understand there are many, many different ways of providing feedback. PID is just a really well-established, easy to understand, and it's what we use in FRC. Now, control theory is nothing new. Once you consider the old steam engine here, there was a problem. If the boiler was really hot, and you open the valve, how fast is the shaft output? Well, it's fast. But as the boiler would cool down, less steam would go through and the shaft would slow down. So somebody invented this ingenious little device called a governor. And you can see there's some metal spheres, they just act as weights, and they spin around, and when they spin around, of course they have a tendency to want to, rise up. So you connect that, you take that motion of those metal spheres rising up or falling down, and you connect it backwards. What do you mean backwards? Well, when they fall down, it opens the valve and lets more steam in. When they rise up, it closes the valve and lets less steam in. As a result, there's a happy medium where it's going to be stable, and the feedback from this is going to keep the output shaft running at a constant speed. That's basic feedback. So you don't need a computer. We use computers because they just make the feedback so much more faster, efficient, and all that. But it's definitely been done by engineers. Remember, I first gave this at Purdue. They're the Boilermakers, so I figured they'd They like that one. Now, switching gears to applying. We talked about sensors, and we talked a little about control systems, and we said there's this PID thing that we use in FRC. So let's use our knowledge of sensors and control theory to actually solve a real problem. Now, in the 2011 season, one of the things you have to do is follow a line. Now, following a line is the quintessential easy way to explain PID. But I want you to understand up front, most of the teams in the last 2 years have used it to control the spinning of their launching mechanisms for either the basketballs or the frisbees. PID is not limited to just following lines. It can be used for just about anything. Wherever you can get data in, you can use PID to control the process. So the problem is, how do we make the robot follow the line? We're going to use feedback, and we're going to derive PID. Everybody know what the derive is? We're going to figure it out. So I have this strange picture here I want to explain because I was confusing some people before. This is like looking down on the robot is what I'm trying to do here. So the green box is the body of the robot. These are the wheels. This circle with the S in it is an exaggerated position of the sensor. And what I want to do is I want to follow that left edge of that line. I want to follow, this is the line. Everybody see that? Okay. And let's say I took some sample data. When I'm completely over the carpet, it's 25, and when I'm completely over the line, 125. So those are my things. So if I wanted to follow a line, easy. I can do this. You know what? I decide I want to be in the middle, 75. And by the way, I'm going to give that a name. It's a set point. That's a key word. Set point, that's where you want it to be set. So if I just say, well, if it's less than 75, turn right. And if it's greater than or equal to 75, turn left. I guarantee the robot will follow along. Right? Have you seen this? Have you been to a Lego tournament where you see robots that do this? It's embarrassing. Because what the robot does is it goes, and it takes it, 45 seconds to go this far. And you can't laugh at it because it's like, jeez, I wish they had an engineer. Call it a jitterbug. Just a cute name. The robot's always turning, or put another way, it never goes straight. Well, if I put it that way, it never goes straight, well, maybe I can fix it. How about if I do this? I say, well, if I'm within 10, my reading is within 10 of my set point, you know what, that's good enough. I'll go straight. Otherwise, I'm going to be turning. Okay. I got to believe this would be somewhat better. I mean, at least sometimes the robot's going to be going in a straight line, right? Okay. Well, wait a minute. Maybe we can make this even better. What about if I'm within 10, I go straight. If I'm within 20, I'm going to turn a little, that's it. And other than that, if I'm outside that range, I'm going to turn a lot. This would probably work better. Okay, I think this is cool. I'm going to go ahead and write this. So, wait a minute. If it's greater than 25 or less than, well, no. If it's, how many lines of code is this going to be? A dozen or so? You got to have less than or equal to, because if I don't, like that first time I showed you 75, it wasn't less than or greater than. I had to have one of them was less, I think it was greater than or equal to, because if I get exactly 75, I'd have a bug in my program, right? So, this is going to be hard. It's going to slow the team down. It's going to take me lots of tries. There's going to be lots of code. It's going to be complex. Somebody else comes to look at it. No. You know what? There has to be a better way. So I started with 2. I decided 3 ranges was better. 5. When will it end? So I get myself a piece of paper and I draw X and Y axis. And on the X axis I put the readings, the limits of my readings. And on the Y axis I put my response. So, and the further I am, the greater my response. Everybody see that? So I started with 1. I'm either doing this extreme. I'm always turning. And then I had one where I'm either turning by a lot, or I'm in the middle. Or I have this one where I'm turning less, so I'm further from the origin of the y-axis. Anybody see a pattern here? Is there a pattern developing here? Is there a simple way to do this? Let me ask you, what would a million ranges look like? Or what would the ranges look like as the number of steps approached infinity and the size of each step got smaller and smaller, approaching zero? It would be what? It would be a line. Everybody see that? Okay. Congratulations. Yeah, it's a line. Oh, lines are easy. I know about those. Grade school stuff, right? Y equals mx. It goes to the origin. I don't even need a b. So, oh, by the way, I snuck that in you. Snuck that one on. Snuck that one in on you. That's the p and did. It's proportional. It's just strictly proportional, right? But what exactly is x? And this is the next major thing we got to grasp. X is the difference between whatever the measurement is and what I want it to be, my set point. It's the error. It's the amount of measured error. And so I have reading minus set point, or in my case, 75 is the error. Now the slope is determined by the programmer, and it's given a special name too. K for constant. Don't ask me, I didn't make this up. Right, but it's K for constant. And P for proportional. So K of P is the proportional constant, which is the slope of the line. So the response now is really what I wanted. The greater the error, the greater the response, the less the error, the less the response. And by the way, this is all the code you need. This is what it looks like. Instead of my dozen lines of is it greater than or equal to or less than or equal to, I get the reading, I compute my error, I respond, I multiply that times my coefficient, whatever that number is, and that's my response out to my motors. Seems a lot easier to me. So if Kp is really small, by the way, what is the slope of a 45 degree? 1, right? So if I have less than 45 degrees, my slope is a number, it's a positive number, but it's less than 1, yeah. No, there's an infinite number of numbers between 0 and 1 that you can choose from. So you have a lot of choices. But if it's really small, if you have a very gradual, you can see, well, it would take a very large change in the error to make a large change in the response. So as a result, if Kp is small, it's fairly gradual. And the robot tends to be more in a straight line. If you make it really large, like the slope of 156, you know, a tiny change in the error is going to be a huge change in the response, and the robot will, you know, make quite abrupt. And the programmer is doing a little engineering, you're finding a balance. So really, you just try different values of Kp until it works well enough. And you know what? If that's it, you're probably done. You've got a great piece of code, and your robot does exactly what you want it to do. Now, that's another nice thing about KID. You don't have to use all of it. If any one of these 3 pieces, you know, solves your problem, you can ignore the rest. But what if somebody throws you a curve? So here's a new problem. Now think about this. If I set Kp nice and gradual, when it gets to that curve, what's going to happen? It's going to miss it. It's going to go out and it's going to be like Tom's customer here. It's going to go crash somewhere. If I set it too high to where it does catch the curve, on the straightaway it's going to be going. So what do we do about that? How can we fix that? Well, I'll tell you what. I got an idea. Let's look at what happens to errors as they change through time. So there's really, I see it, 3 different cases. There's, I'm either too far one way, too far the other, or right where I want to be. Now, if you look at the sum of the errors in these cases, you know, I'm getting about 50 if I'm too far one way, or 50 if I'm too far the other. I notice that these quickly add up. They start becoming really big, pretty fast, especially if I'm sampling it like 2 times a second or 10 times a second. This number is going to get really big if I keep adding 50, 50, 50, 50. Okay? And the same here. The only difference is the the sign, so I can tell which direction, which way I'm missing. But an interesting thing happens if I'm right on course. I'm going to normally get a little error, but it's going to be some on half, some on this half, some on this half. And over time, they should add up to nothing. They should cancel each other out, right? If I just have normal variation, I'm going to have a little pluses and little minuses. So that's kind of interesting. So by the way, that's not that 1/92. That's the integral. That's the I in PID. And what it does, it builds up really rapidly the longer you're off target. The sign will tell you which side you're off or which direction you're going. If you're too fast, too slow, too left, too right. And if you don't need it, the integral will tend to add up to 0 over time, which means it doesn't affect the proportional part. All of that means you can have your response, it can rapidly change to changing conditions, like the line that suddenly curves. Now, so far we have just this, AP times the errors, right? That was y equals mx. And then everybody knows sigma, the sum of the errors. It's the integral. Okay. But, wait, what happens if you overstretch a spring? Does it come right back to where it's supposed to be? What happened? And when it didn't stop where I wanted it to, it kind of, you get this problem that's called overshoot. That's where it's built up so fast, so big, that the robot tends to overcorrect, totally misses the line, and you end up like Tom's customer again. So sometimes the integral is more of a problem than a solution. How can we combat that? Well, I'm not going to sneak one in on you anymore, because you probably guessed it. That's the d in PID. It's the derivative. So rather than explain it in technical terms, what we really need is something that will suddenly counteract that growth in the integral when the sensor gets back to the set point, or when I get back to where I want it to be. And it's simply the change in the error. It's just, in the simplest sense, it's just the current error minus the previous error. So I have a demonstration here, and what I'm trying to show you is, here's my sensor at 4 different times, time 1 to 4, and the number above it is the reading. And you can see, I'm consistently getting the same error. So I'm reading 25 minus 75 is minus 50. Okay. But at time 4, it suddenly snaps back. Now you see my integral grows up, and it's pretty big. And at this point, the error is positive, which tones this down a little bit, but not very much, right? This is still pretty big. I'm probably just relying on that, I'm going to overshoot that line. But look what happens. The error doesn't change in the first 2 cases, from here to here, and from here to here. My reading didn't change. But current error, 25, minus previous error, minus a minus 50, is a positive 75. And by the way, you don't have to worry about the signs. They always work out just for you. That's kind of, I always think that's kind of magical. The signs take care of themselves. And as a result, it really tones it down. So if I add I and D together, instead of minus 125, I've got minus 50. So what the derivative then does is it's D derivative D dampener. It dampens the overshoot potential of the integral. So this is how D counteracts it. And you'll notice that, these are nice and close, but we can probably make it better. So we assign coefficients to the integral and the derivative. Those are tuning parameters. You can play with them. They're fun. I've done it many times. It's kind of a fun challenge to make it work just perfect. By the way, if you're using LabVIEW, you don't have 3 coefficients. You only have 1. So they even simplify it more. LabVIEW is a nice tool. I love it. So this is it. This is how simple it is to write a PID algorithm. And if you do this with any of your sensors, you can get, precise control and complete repeatability. Which are pretty nice to have in an FRC robot. So you get the reading from the sensor. Oh, you start the program, and at some point you have to define those three things, or four things: your set point and your coefficients. And then when you're running the program, you just read your data, compute your error. Integral is the running sum of the errors, right? Isn't that what that is? Derivative is just current error minus last error. Then I swap those two out. I compute my response, output the motors, go back and do it again. Everybody understand how simple and easy that is? How it cleans up your code and how it makes your robot very precise. Like I said, typical use on this in FRC the last 2 years has been rotational speed of your shooting mechanism, so that after you feed a ball or a frisbee through it, obviously it's going to slow down. You want it to come back up to speed but not overshoot it, so that you get the same RPM, the same speed, and you get a consistent output from your launching mechanism. This is how you do it. It's very simple. And here's the fancy formula that you'll find in textbooks, but not you know it. Okay, so question? Yes.
I'd say I think my team understands the necessity for sensors, but we are lacking sort of intro projects to get into it. I was wondering if you had any ideas of ways to get our feet wet to start practicing using these things. You had said one earlier on the following line code. We did that a couple of years ago. But are there any other ones you know of that you suggest?
I like to build subsets of robots, like maybe just a pivot point and an arm, and have a potentiometer on it, and see if I can move it 100 times. It's easy to program a robot to do something 100 times, and see if after the 101st time, if it's still at the same angle. It's very simple. All you need is a motor, a gear train, and a sensor. And you can practice with that, and you'll find when you're doing those kinds of things, there's all kinds of little subtleties, like is your gearbox a little bit wiggly? Is the sensor mounted nice and firm? There's all kinds of little details like that you can learn lots of things from. Now, you don't have to build the entire robot. For the accelerometer, I think the fun project is build something that no matter which way I tip it, it always levels itself. You could do something with a gyroscope to what would be a good one for that? I'm trying to think. What we did in freshman engineering lab was balance a couple of blades that went this way. A lot of it is just, take the time to actually connect it up, become familiar with it, see how easy it is to use. All the tools are there, the wiring diagrams, you just have to dig a little bit. And then start thinking about now, how could I use this to make it easier for my drivers? How could I, remember when 2 years ago, 3 years ago, we had to come up to a certain height and hang things on pegs. How can you make your lifting mechanism so that they can push once and it goes to the first height twice or something like that? And think about how you can control that with the sensors that we have. Questions? If anybody's interested, you're wondering, somebody gave me an industrial PID controller. It is so industrial it does not have an on-off switch, and it does not have a cabinet. It's meant to be mounted on a piece of sheet metal and poke a hole in it. But to go into menu, where's setup? There's my set point. Okay. And set point menu, hit parameter menu. Can you see this? If I go into my hit parameter menu, there's my proportional, my interval, and my derivative. So I'm not making this stuff up. The other thing is I have from an ancient system, there's a gauge that actually measures, the bottom one is a measurement of your set point to make sure you walk by on the factory floor or something, make sure the set point is set correct. And then there's something here that just says process, which could be whatever sensor that is. But it is widely used in industry because it is so simple, because it is so effective, and because it is so easy to implement. Even these primitive, this is older than the IBM PC. It's an Intel chip in there, but it was before the invention of the 8086 architecture. So this has been around a long time, and definitely something you can use to make your team give it a competitive edge at the next regional. Okay, I think we're way past time, so I gotta let you go. Thanks so much, everybody.